Good morning. My name is Elisa Gorla, and it is my pleasure to introduce today's plenary speaker, Kristin Lauter. Kristin studied at the University of Chicago, and then she held positions at the Max Planck Institute in Bonn, the University of Michigan, Lumini, and MSRI before joining Microsoft Research. And she currently is principal researcher and research manager at Microsoft, and also affiliate professor at the University of Washington. Her areas of interest are, broadly speaking, number theory and algebraic geometry, and she's specifically interested in the applications to cryptography, coding theory, and machine learning. She has a large number, not only of publications, but also of patents, so a real applied mathematician. And she received many prizes and honors. I'll just mention a few. So she's a fellow of the AMS, and she was awarded the Selfridge Prize in computational number theory. Kristin is very committed to diversity in mathematics. She's a strong sponsor of it. So she served as president of the Association for Women in Mathematics. And also she was a council member, or maybe she still is a council member. She's also the lead PI in the grant that the NSF has to sponsor, that they have with NSF to sponsor networks for women in mathematics. And she's in the Committee for Women in Math at the IMU. She's on many advisory boards. She's a trustee of MSRI. And I'll say in closure a couple of words about her research. So some of her most important results, I would say, are in homomorphic encryption, elliptic cryptography, and in isogeny-based cryptography, which is one of the candidates for post-quantum cryptography. So she will explain this immediately in her talk. And within isogeny-based cryptography, she introduced a hard computational problem, which is the topic of this talk, which is at the base of the security of these proposed crypto systems. And in closure, I just quickly say that if people are interested in post-quantum crypto and specifically isogenies, there will be a mini symposium this morning and tomorrow morning, which deals with the same themes, just more specialized. So with this, thank you, Kristin, and I leave the floor to you.
Thank you. Thank you very much for the generous introduction. Thank you for the invitation to speak here, and thanks to all of you for coming. So I am especially pleased to speak in a conference which is on applications of algebraic geometry. I was thrilled when those of you who put together the special section for SciAm finally incorporating some of the other parts of mathematics into the world of applications. So it's been just really great to see the growth of this community, and so impressive to see this conference with more than 750 people here now, all these sessions. So you guys all deserve a round of applause for getting this section started and getting this conference going, and the journal as well. Don't forget about the journal. Okay, so I'd like to speak to you about one aspect of my research, which is supersingular isogeny graphs in cryptography. And as Elisa mentioned, it's particularly relevant these days in the context of post-quantum cryptography, so I'd like to explain this a little bit. And at the end, I'll also give a pointer to the ongoing session. There's 4 parts to the isogenies in cryptography special session at this conference, and 2 of them, one of them this morning, and the 4th one tomorrow, so in case you've missed them so far. So I didn't want to assume that everyone here is a cryptographer. I don't think they are, so I just want to start with a little plug about cryptography. So we often think of cryptography as being the science of keeping secrets. But it's actually even more than that. It's beyond encryption for preserving confidentiality. There's all kinds of other things that we're concerned about, for example, authenticity. And there's a number of tools that cryptographers have come up with over the years to help provide security for online commerce and all kinds of other things. But besides encryption, decryption, which is the thing that most people know about, digital signatures is a major building block, and key exchange is a major building block. So these key exchange, I'll give you an example of later in my talk. Key exchange in public key cryptography is just the process by which two parties can exchange information publicly and yet agree on a common secret. And then signature schemes allow parties to authenticate themselves, and encryption is, of course, for preserving confidentiality. So most of you probably know or have heard of or have taught or whatever the major examples of public key crypto systems. RSA and RSA is about 40-year-old proposal, which uses the hardness of factoring to create crypto systems. Diffie-Hellman systems are based on the hardness of the discrete logarithm problem in the multiplicative group of a finite field. And then elliptic curve Diffie-Hellman is the elliptic curve version of that. And then there are digital signature versions of both of those. So the typical applications that we think of would not be possible if it weren't for a process of what we call standardization. So standardization in cryptography can take many different forms, and it typically will result in some type of a standard, such as for secure browser sessions, something like the TLS standard. And these are like industry-wide standards or sometimes government standards that industry players that want to implement cryptography need to follow. And that's what allows us to create systems that are interoperable. So this process of standardization is very important. And I like to think of it as having a couple of stages. So the first stage has to do with what we're doing here. Mathematicians in industry, government, and academia working on hard problems, basically proposing hard problems, thinking about how hard they are, trying to attack them, then trying to model the attacks, trying to understand how fast the attacks run so that you can set the parameters to be secure. And then once everyone in the research community kind of agrees on the strength of the system or the running times of the best known attacks, then those parameters can kind of be standardized. So that's kind of an initial stage. But after that, what happens is equally complicated and lengthy process. You have to have interested parties in industry, government, who come together to create draft standards, and then these things are reviewed. Often there can be open competitions, like NIST, the National Institute of Standards and Technology in the US, has run open competitions to determine new hash functions, new block ciphers, now new public key crypto systems. And once the kind of standardization process has run its course, hopefully what comes out at the end is some standards like this kind of thing, that TLS for secure browser sessions, or SMIME for signed encrypted email, IPsec for virtual private networking, X509 certificates, these types of things. Now, once you have kind of a framework of standards in place, then after that, what often happens is that's when the regulators come in, and regulation and government requirements will decide which of these systems actually must be implemented or should be implemented in order to meet certain qualifications, for example, in the health industry or in the finance industry. So these examples that I've put up here on the slide are just a few of the standards that are out there today governing the use of public key cryptography. So public key cryptography that's deployed in practice today is based on these systems. So I mentioned RSA. RSA is based on the hardness of factoring large integers. The discrete logarithm problem, just most people probably know what it is. Oops, I did not want Siri talking to me. Just wanted to know what time it was. The discrete logarithm problem is in any just think of a cyclic abelian group. If you have a generator, let's call it little g. The discrete logarithm problem, and I'm thinking of this as a, in case I didn't say finite cyclic abelian group. Given any element of the group, you want to know which power of the generator it is. That's the discrete logarithm problem. So if it's a multiplicative group, it would be a power, but if it's an additive group, it would be a multiple. It would be the scalar multiple that you're looking for. So the discrete logarithm problem in ZP star is the foundation for the typical traditional Diffie-Hellman. But you can also have a discrete logarithm problem in the group of points on an elliptic curve. So there you might typically have some, you take an elliptic curve over a finite field, and I'll show some equations later for elliptic curves that we typically work with. And you'd have a generator for some, it might not even be the whole group of points of the elliptic curve over this finite field. It could just be a cyclic subgroup that has large prime order. And so you can have the discrete logarithm problem in that group. And then finally, there's another construct that was introduced into cryptography in both positive and negative ways in the early 2000s, which is the Weil pairing on an elliptic curve. And that can be used for constructing a lot of interesting cryptographic primitives as well. So these are all the kinds of public key cryptography that are deployed in practice today. And in fact, when I went to Microsoft in 1999, and I spent my first 5 years working on getting elliptic curve cryptography implemented and optimized and deployed in Windows. And it finally started shipping in Windows Vista in 2005, roughly. So all of these systems are fairly widely deployed worldwide in the industry. And so why would I be talking to you about anything else? I've given gazillions of talks on elliptic curve cryptography. So, but we have kind of a new disruption coming, which is the, let me come back to this, what I'll call the quantum threat. So the problem is that for all of these problems that are currently deployed, the classical algorithms that we know for solving them are, they run in, at best, sub-exponential time. So exponential or sub-exponential time. Whereas once a quantum computer can be built at scale, we will actually have polynomial time algorithms for solving all of those problems. So let me just go back to this slide. So I realized from giving talks to very, very sophisticated mathematical audiences that I would often get to the end of the talk, and I would realize that these very, very famous sophisticated number theorists really had no idea what I meant by a hard problem. So I'm just going to give, this is a very basic idea. It's not the nitty-gritty details. But when we say a hard problem, a hard math problem in cryptography, we kind of have a commonly agreed upon point of view, which is that it means that if it takes you m bits to represent the problem, for example, if there's a number n, which is p times q that you want to factor, and m is the number of bits that it takes to represent n, then the best algorithm that you know to solve the problem, for example, factoring, if it runs in exponential time, which means essentially proportional to 2 to the power m, that's an exponential time algorithm. Or you could even have better algorithms that are run in less than exponential time. We call them sub-exponential algorithms, and I wrote like the formula for an example of what we call an L1/3 algorithm, which would be the exponent, but the power is m to the 1/3 power, typically times some constant, and then times log m to the 2/3 power. So if a problem is hard enough so that the best algorithm that you can find to solve it takes either exponential or sub-exponential time, then it's typically good enough for cryptography. What happens when you have polynomial time algorithms, which means the running time is a polynomial in M, is that typically, of course, when we say these exponential, sub-exponential polynomial time algorithms, we're forgetting about all of the constants and often forgetting about the log factors and things like that. And those can be significant in practice. They can alter the running time. And so, of course, you can't say what the concrete running time is just by saying what the asymptotics are. But typically, when you have a polynomial time algorithm to attack these systems, it's going to be efficient enough to run it in practice, and that means you typically will not want to deploy such a crypto system. Another way to think about it is that when you deploy cryptography, it's all about your resource use. So how many bits does it take you to represent the problem, to write down your public key, to send a ciphertext? How many bits does it cost you? How much time does it cost you to do the computation of doing encryption, decryption, or whatever else it is? And so you want to minimize that ratio of how much time you have, time and resources you spend. You want to minimize the resources that you spend in order to get a given security level. So these are the general context for everything I'm going to say from here on is that we want, in cryptography, we want to avoid using problems which have polynomial time solutions, and we look for problems for which the best algorithms that we know are exponential or maybe sub-exponential. And the quantum threat is that even though the classical algorithms, for example, for RSA, the best known algorithm is the number field sieve, which is a sub-exponential algorithm, heuristically like an L1/3 algorithm. But the best quantum algorithm is Shor's algorithm, which was proposed in the 90s. And we do not have, so just to be clear, we're making progress, people are making progress on building quantum computers, but we do not have quantum computers yet. So all of these numbers here on this slide will be the attack times once there exists a quantum computer at scale that could be used to factor. And so, for example, for using Shor's algorithm for factoring, we estimate that the factoring algorithm will take something like 4m cubed time, and it will require 2m logical qubits. Whereas to attack an elliptic curve crypto system will take something like, so these estimates are from Prus-Zalka from 2004. They estimated something like 360 m cubed time and 6m qubits. So we actually did kind of a refined analysis by using counting Toffoli gates and things like that in a paper at AsiaCrypt last year that gives slightly refined constants and extra terms. But by and large, these are the attack times that you should expect on these systems once we have a quantum computer. So the conclusion is that they will not be resistant to quantum attacks. And in preparation for this, what we've seen actually is so this is just a little snapshot of the evolution of the deployment of elliptic curve cryptography in industry. So it was around 2006 when the Suite B requirements were released by the US government, which required the use of elliptic curve cryptography to protect, at least for government contractors in the US. So it made it very attractive to implement elliptic curve cryptography in industry if you wanted to sell any software to any government contractors in the US. So the Suite B requirements were very significant in pushing the deployment of elliptic curve cryptography. But in 2016, they issued revised guidance. And instead of the minimum size for elliptic curves being 256 bits, they required minimum size to be 384, and they also advised that the adoption of ECC was no longer required. So that was a hint that maybe quantum computers are coming, or maybe they've made some progress in the classified world on attacking some of these things. So at around the same time, in the US, NIST, the National Institute of Standards and Technology, announced an international competition, which is currently ongoing, to select new post-quantum solutions. So PQC, post-quantum crypto, whenever you hear somebody say post-quantum crypto, what they're referring to is trying to come up with crypto systems which will still be secure once there is a quantum computer at scale. So this competition, the NIST competition, is expected to be around a 5-year process. There's a number of submissions to the NIST competition based on hard math problems. And at least, so 3 out of 4 of these are represented in special sessions at this conference, which I thought was very cool. Very pleased to see that. So what I did here was to try to give a timeline of how long these problems have been around by just stating when the problem was introduced. So code-based cryptography was introduced by McLeese in 1978. So you can see it's actually been around almost as long as RSA. And in cryptography, you just should typically think of a problem, the length of time that it's been around, as a kind of an important indicator, because people have had that much time to think about how hard it is and keep trying to come up with new attacks. So code-based cryptography has been around for 4 decades now. And there's a session on that at this conference. So multivariate cryptographic systems has been around for maybe about 30 years, introduced by Matsumoto Imai. It has gone through a lot of iterations of proposals and breaks and improvements and stuff, but there are still valid submissions that remain unbroken to the NIST competition for that as well. So multivariate cryptographic systems are based on the hardness of solving polynomial systems of equations in many variables and many equations and nonlinear, of course. Whereas code-based cryptography is based on the hardness of decoding random linear codes. And in order to set up a code-based crypto system, you also have to kind of use some code that you know how to decode and then disguise it as a random linear code. So it also depends on being able to disguise a code in a way that cannot be discovered. So the third proposal is very close to my heart. So lattice-based cryptography was first introduced in mathematics by Hofstein, Pfeiffer, and Silverman with the N-truth system in the mid-90s. So that N-truth system, they actually formed a company, and those systems have been around for more than 20 years. But actually, the hard problem that they're related to, which is the shortest vector problem in general lattices, has been around for even longer. And there are lots of algorithmic contributions in lattice-based cryptography that go back more than 30 years. I'm sorry, on the hardness of lattice problems, not necessarily in cryptography, but Connon's algorithm and LLL go back to the 80s. So lattice-based cryptography has already also been around for quite some time. And actually, full disclosure, I spend most of my time these days on lattice-based cryptography because I work a lot on homomorphic encryption, which is based on lattice-based cryptography. So the final topic on my list is what I would like to describe to you in more detail here today, and this is where the algebraic geometry comes in. So there's algebraic geometry in the first two as well. Actually, code-based crypto, it has been proposed to use algebraic geometry codes for a code-based crypto, although there are better attacks on those known. And that was one of the things that I worked on in my thesis in graduate school, was algebraic geometry codes from surfaces, from K3 surfaces, because my advisor was an expert in K3 surfaces. So that one is very close to my heart as well. But so supersingular isogeny graphs were introduced in 2005 at the NIST hash function competition, the first workshop that NIST ran on to select a new hash function by myself with my co-authors Dennis Charles and Eyal Goren. And so I'd like to spend the rest of my time talking about this topic. So the high-level takeaway from this slide, though, is that all of these problems, we think that they're resistant to quantum attacks. But you also have to remember, they also have to be resistant to classical attacks as well. So you have to still keep thinking about classical attacks for all of these problems, because they're not as well studied as the ones that we have been using for all of these decades. So supersingular isogeny graphs was proposed in a paper with Charles and Goren called hash functions from cryptographic hash functions from expander graphs. So in that context, what do we meant by an expander graph? So a graph is just given by a set of vertices and edges. And in that context, what we wanted was we wanted to use expander graphs, so graphs that have good expansion properties, and that were also, just for convenience, we assumed that they were k-regular, so they had k edges coming out of every node. They're undirected, and the key point is that they should have no efficient routing algorithm. So what is a routing algorithm? Routing just means if you take two random points in the graph, that it's hard to find a path between these 2 points. So that's what I mean by routing. You could call it path finding. I often use those words interchangeably. So what we were proposing was a new construction of cryptographic hash functions. So I'll tell you what it is in just a second, but first, what is a cryptographic hash function? Well, a hash function in general is just a map that it just maps bit strings to bit strings. And in of some finite length to some other fixed finite length. And there's a couple key properties that a hash function should have in order to be deployed in practice. First of all, it should be very easy to compute, very fast. And you could even see in the hash function competition that took place more than 10 years ago that there's a strong bias towards selecting a hash function that was not based on mathematical operations, which are typically much, much more costly than kind of symmetric key type of operations, because the requirements for hash functions are very, very stringent in terms of being able to be efficiently evaluated. And that's because they're used everywhere. They're used inside of so many protocols, and that if they were much more costly to compute, then it would end up kind of slowing down everything. So they need to be easy to compute. And when I'm talking, the hash functions that I'm talking about now are unkeyed, so you don't need to have a secret key in order to evaluate them. You can specify them, and anyone can evaluate them. And, but the properties that they need to have in order to be useful in cryptography are that they should be collision resistant. And I'll say what I mean by that in just a second. And also, it's good not to have a bias in the output. And that's why the expansion property of the graphs was important. So you like to have a uniformly distributed output. So by collision resistance, we just mean that it's computationally infeasible to find two distinct inputs that hash to the same output. So you could see from my definition of hash function, if you had a very, very long bit strings being hashed to shorter bit strings, which is often how hash functions are used, obviously there's going to be some collisions. So it's not saying that there are no collisions, it's just saying that it's very hard to find a collision. And we say that a hash function is preimage resistant if given any particular output of the hash function, it's hard to find an input that hashes to that output. So what was the cryptographic hash function that we proposed from expander graphs? You just take this k-regular graph, and in order to instantiate this, vertices actually have to have labels, which might seem like a trivial statement, but it's actually a non-trivial requirement. It can be very difficult to come up with labels, especially if you're working with very complex algebraic geometric objects. And the hash function will simply have a specified starting point in the graph. So you can have a family of hash functions. Each one has a different starting point, but the hash function, each hash function itself is specified with a starting point. And then the input to the function is a bit string, and you just simply divide this bit string up into chunks that can be used to, as directions for walking around the graph. So each block of the input is kind of specifies which edge you should follow at each step of your walk. So you're going to start at some point, you're going to walk around this graph, and you're going to use the input string as the directions for walking around the graph. And then when you get to the end of the walk, the output is going to be the label of the final vertex of your walk. And one thing that's really important is that no backtracking is allowed. So if you go forward in this walk, and then if you're allowed to go backwards, you could very easily create collisions because you can just go forwards and backwards at 2 different points during your walk, and that will still have the same output, and you don't want that. So on these walks, no backtracking is allowed. And so this is the general idea of hash functions from expander graphs. And so in particular, okay, so here's just kind of an example. If you have a 3 regular graph and you're not allowed to backtrack at any step, that means you only have 2 choices coming out of each vertex. And so you have only 1 bit is necessary to specify the next step of your walk. So 3 regular graphs are particularly easy to implement because you can just read off the bit strings bit by bit to walk around the graph. So in this case, the arrows here are just indicating the walk. They're not indicating that it's a directed graph. You read the first bit as a 1, the second bit as a 1, and the last bit is a 0. That's how it works. So this idea of using random walks on expander graphs is a very standard idea from computer science for complexity theorists, and it's a good source of pseudo-randomness. This has been used, it's been around for ages. So the only really new thing that we introduced was this idea that you would want to try to find expander graphs where routing is actually hard so that you can't invert these walks. And so we wanted routing, pre-image resistance and collision resistance. So we wanted to be hard to find collisions and to find paths. So just to kind of get the general idea across, I always think it's good to mention a really bad idea for a graph to use. So if you wanted to use a hypercube in n dimensions, just think of it as all the bit strings of length n are the vertices, and 2 vertices are connected if they differ by just 1 bit. So that's a hypercube. And obviously, this would be a really bad choice because it's really easy to route in this graph. Just take 2 bit strings, and to get from one to the other, all you have to do is flip all the bits that are different. And you can flip them in any order, so you have lots and lots of paths. So that's not a good idea for this type of construction. So what kind of graph did we want to use? So the 2 graphs that we proposed were actually optimal expander graphs, Ramanujan graphs, in fact, the Lebowski-Phillips-Sarnak graphs, and then the supersingular isogeny graphs. So Ramanujan graphs are optimal expanders, and I'm not sure if I'll have time to get into too much detail about the Ramanujan property of these graphs. But, and to find a collision is, again, it's to find 2 distinct paths that end at the same place. So if you think of these graphs as being undirected, 2 paths that end at the same place, that's the same as finding a cycle in the graph. So one of the things you can do is to also put conditions to try to make sure that there are no short cycles in your graphs. So the graph that I said we proposed 2 graphs, but I'm going to focus on the supersingular isogeny graph right now. We call them the Peiser graphs. They were introduced by Arnold Peiser in the 80s, actually, but also studied by Mestre. So some people call them Mestre graphs. So here's what the graph is. So now you'll hear elliptic curves again. It's not the same as the standard elliptic curve cryptography, because here elliptic curves are going to be, each of the vertices in the graph is going to be an isomorphism class of a supersingular elliptic curves over in characteristic p for some large p. P will be of cryptographic size, so it'll be hundreds of bits. And what is known is that for each isomorphism class of supersingular elliptic curves, there is a representative of it which is defined over either fp or fp squared. So in practice, you can think of each vertex as being this isomorphism class, but being represented by a curve with a J invariant, which is either over fp or fp squared. And the nice thing about elliptic curves is they have really nice labels, which are the J invariant. So J invariants classify elliptic curves up to isomorphism over the algebraic closure, and they're very, very easy to compute. So even though when I was in graduate school, elliptic curves were very complex abstract objects, in cryptography they're typically taken to be very, very concrete, given at least in characteristic not equal to 2 or 3 by a short Weierstrass equation. So you can just think of elliptic curves as being like y squared equals x cubed plus ax plus b, where a and b are in some base field. And here, the field is, fp or fp squared, where, like I said, p is of cryptographic size, so it's definitely not equal to 2 or 3. So we can take the short Weierstrass form. And then the J function, the J invariant is just this, rational function in the coefficients of the defining equation. So it's very, very easy to compute. So I've told you what the vertices of this graph are. Now, the edges are going to be isogenies between elliptic curves. So isogenies are just rational maps between elliptic curves that actually preserve the group structure. So they take the identity to the identity. And again, we're going to make a little bit of a simplifying assumption here. All the isogenies that we consider are going to be separable. Because what we want to do is we want to take very small degree isogenies. Again, they're actually going to be typically degree 2 or degree 3. And the characteristic is extremely large. So definitely the degree of these isogenies is prime to the characteristic. And so we're talking about separable isogenies. And so what that means is that separable isogenies are completely determined by their kernel. The degree is just the size of the kernel. So you can just think of, elliptic curve is this geometric object, but it has a group structure as well. So you can think of an isogeny as just being given by a subgroup of points on the elliptic curve. So for example, if it's a 2 isogeny, that means you're just quotienting by a subgroup of order 2, which is given by a single 2 torsion point. And in general, for L prime, different from P, there are L plus 1 choices of the subgroups of order L, and so this gives you an L plus 1 regular graph. So there's also a couple of other really beautiful properties of these graphs that come from the fact that they're supersingular. And one of those is that they're Ramanujan. So we can actually make them into undirected graphs if you assume that P is congruent to 1 mod 12. There's beautiful theorems in number theory that we use to try to understand these graphs better. So one is a During correspondence, which means that instead you can actually, the way Peiser introduced these graphs was not in terms of elliptic curves at all. It was in terms of maximal orders and quaternion algebras. And the correspondence here, again, depends on the property of this elliptic curves being supersingular. So I did not say what supersingular meant yet. There are several different definitions. Many of you probably know it already, but supersingular elliptic curve in characteristic P, you could think of as meaning that there's no P torsion. P torsion is empty for all extension fields. But another way to characterize it is that the endomorphism ring of the elliptic curve is actually a maximal, it's non-commutative. It's a maximal order in a quaternion algebra. And so this correspondence is called the During correspondence. And unfortunately, one of the things that we have found in working in this area is that it's actually very hard to make this correspondence explicit. So even though the During correspondence is known as a theorem, it's not known in practice constructively. So the other nice way that the supersingular property is used here, besides being a Ramanujan graph, is the Eichler class number tells you how big this graph is. So the Eichler class number tells you that it's roughly of size p over 12. It's the integer part of p over 12 plus a small 0, 1, or 2. Okay. So this is just one slide to convince you that these graphs are very, very easy to implement in practice. So if you take, I told you the cryptographic application would be a hash function. If you take a walk, you're going to need to start at some elliptic curve. You're going to need to compute, let's say, L equals 2. You're going to need to compute 2 isogenies. Here's a formula for the elliptic curve that you get when quotienting by a single 2 torsion point of the form r comma 0. And the formula for the isogeny as well. So you can see these are just very simple rational functions that are easy to compute. So at this point, what I'd like to do is to show you a picture of an isogeny graph. So this picture actually appeared in Science magazine in 2008. I gave a talk on the supersingular isogeny graphs at the joint math meetings. I think it must have been 2007. And Dana McKenzie, who's a science writer, was in the audience. And so he wrote an article about the ongoing hash function competition. And he wrote an article about our hash function based on supersingular isogeny graphs. And he published this picture, which we produced for him, which has, as you can see in red, this is a cycle, and in blue, this is, you know, a path. So slightly bigger picture here. So let me just explain this graph a little bit, because it looks pretty messy, probably. So it's P here, I think, is something like 25, 21. So if you take P and divide it by 12, you get roughly around 200. So you're looking at a graph here that has 200 vertices in it. And the idea is that this is supposed to look as messy. It's supposed to look messy, because the idea is that if you were to scale up P up to, like, let's say 256 bits, imagine how intractable the problem is of finding paths. So take 2 random vertices, and that's what we showed with the blue path here. Just take those 2 vertices that are the endpoints of the blue path, and you can see that there's no real direction in this graph. There's no obvious way to find your way from one of these nodes to another. So that's the basic hard problem underneath. And same thing for the cycle. There's no obvious way to find cycles in this graph. So I also like to show this picture because I think it's a very beautiful graph, and it's nice to have a picture of the graph of such sophisticated mathematical objects appearing in the popular literature. So behind all of this, one of the things that I'm not going to talk much about today is that, you know, the context in which Master was interested in these graphs was because so the adjacency matrix for these graphs is actually the what we call the Brandt matrices. They are give the action of the Hecke operator on spaces of modular forms. So people that do computations of modular forms, even people doing like modular symbols and things like that, are very interested in not exactly these graphs, but at least these matrices from the point of view of finding bases for spaces of modular forms. So there's a completely different application and interest in this area that intersects here. So you could even call this the Hecke graph, because it's actually the graph corresponding to its adjacency matrix gives the action of the Hecke operator on spaces of modular forms. So it's a very beautiful mathematical object in that sense. So the next thing I wanted to do is to talk about a few other applications of supersingular isogeny graphs that have come up since we introduced them. So it was almost 15 years ago. I realize that doesn't stand up very well to 40 years for code-based cryptography, but still, it has been around for a while now. In 2011, Zhao, DeFeo, and Plu introduced key exchange based on supersingular isogeny graphs. And there was also an encryption system and also signatures, so Galbraith, Petit, Silva signatures, and a number of others that are in the process of being proposed now. In fact, even some presentations at this conference. So I'd like to kind of give you the idea of the key exchange based on these graphs. So when, I may come back to this picture. So what we're going to do is we're going to do a particular setup that's involves choosing a prime in a very special way. So for example, if we take two small primes now, LA and LB, sorry about the notation, just LA is going to be 2 and LB is going to be 3. So just some big power of 2 times some big power of 3 plus 1. Basically, that's what your prime is going to be. It is more general than that. You can let LA and LB be other small primes. But in practice, they're just 2 and 3. So now, if A and B want to exchange a key, so the idea of the Giao-Dufay-Plout system is that A and B are both going to publish, their public parameters are going to be generators for the torsion that's associated to them. So LA is for A and LB is for B. So A is going to pick generators for the 2 to the M torsion, and B is going to pick generators for the 3 to the N torsion. The M and the N are the powers that those 2 and 3 appear in the prime there. So that's public. So those are generators for the torsion. And then what they're going to do to exchange a key, they have their own secrets. You could think of them as being just random integers, which are going to be the multiples of the torsion points that they're going to use. And so A is going to have random integers, call them MA and NA. And A is going to compute now a secret isogeny. And A will do that by just taking MA times PA and plus NA times QA. And that generates a subgroup, which has order, if LA was 2, has order 2 to the M. And what A is now going to do is quotient the elliptic curve by this subgroup. And B, on the other hand, is going to do the same thing, but with the other prime, LB, and the other generators, the generators that B has published. So now A and B have now each computed their own special secret isogenies. And what they're, now how is this going to result in a key exchange? So let me just kind of go back to this picture so you can kind of follow along. A and B have just computed the first arrows in this diagram. These are their secret isogenies. And what they're going to do then is to also publish the image under their secret isogenies of the other party's generators. And that will be necessary in order for the other party to be able to complete the diagram and so that they can both end up computing the same curve. So after what they're going to do is they each, it's much like Diffie-Hellman key exchange in the usual multiplicative group of a finite field or group of points on an elliptic curve. Each party has its own secret, and then they see some other information from the party they're trying to exchange information with, and they use their own secret to compute the next, the final step of the key exchange. So A will use MA and MA and NA and apply that to the torsion points that B has provided the image of, and vice versa. And so both parties can then end up computing a subgroup that really is just the quotient. E is quotiented by that subgroup to give you this curve EAB. They've just computed that subgroup in 2 different ways, but it's the same subgroup. And separable isogenies are determined by their kernels. So this is actually the same curve. And the J invariant of that curve will be the shared secret. So this is a very beautiful idea for a kind of a key exchange. And so one thing that was interesting is that when Giao, Dufay-Plout published their paper, they stated a collection of 5 hard problems underlying the hardness of this key exchange and some related constructions. And And none of those hard problems was routing in supersingular isogeny graphs. And nowhere in the literature was it actually related to the hardness of pathfinding in supersingular isogeny graphs, even though I think to many of us it was fairly clear that it is related. So the security of the key exchange actually depends on the hardness of pathfinding in both of these graphs, the LA isogeny graph and the LB isogeny graph. So for example, 2 and 3 isogeny graphs. And the way that you can see that is there's kind of 2 steps. So in fact, this was the output of my working group at the Win4 conference in 2017. So the result from Kostas, Feigen, Meiser, and Puskás that we got was showing that if you can solve the pathfinding problem, then you can break the key exchange with extremely high probability. Your probability of failure is p to the minus 1/2. And so if p is something like 700 bits or something like that, your probability of failure is overwhelmingly small. And for us, we always had p was 256 bits, but even at 256 bits, the 2 to the minus 128 is not too shabby in terms of your odds. So how do we prove this theorem? And again, this was essentially probably known in some ways to the experts. But one thing that's kind of shoved under the rug is that in this key exchange, there's a step which I said without saying how to do it. And that is you have an isogeny of degree 2 to the, like LA was 2 and LB was 3. So 2 to the m and an isogeny of degree 3 to the n. And these are primes of cryptographic size. So if you take a prime of size, let's say, 700 and some odd number of bits, you're talking about n and m are somewhere around 300 or more bits. So now you're talking about an isogeny of degree like 2 to the 300. Well, using Velu's formula, you cannot write down such an isogeny. That cannot be done in today's world anyway. So what you do instead is to think of it as a walk in the isogeny graph that I showed you before for the hash function, and this is how it's done in practice. And lots of work has been going into doing these kinds of walks efficiently for the key exchange. But so what that basically means is that each of these isogenies, even though I described it as an isogeny of degree 3 to the m, where it was generated by 1 point, in fact, if you write down a bunch of simple group theory, you can go back and forth between walks with no backtracking and isogenies that are used in this context with certain properties. So that was the first step, is to just specify precisely that correspondence. But secondly, the interesting thing is to look at the sizes of the parameters here. So if you look at this prime that we picked, p was 2 to the m times 3 to the n plus 1. And one thing I'm not sure that I said, but n and m are chosen to be roughly of the same size. So what that means is that m and n are both roughly half log p. So log p is essentially like m plus n, and they're roughly the same. So each of m and n are about half log p. That means that when you are walking around this graph, and you take m steps or you take n steps, you're walking about half the diameter. So one thing that I haven't talked a lot about the properties of the expander graphs and the expansion, but the diameter of these graphs is essentially, it's not precisely known, but it's somewhere between log p and 2 log p. What that means is diameter is just the smallest number so that there exists a path of that length between any 2 vertices. And so that means that if you take a path of length half the diameter, most pairs of vertices will have no path of that length between them. So if you're in doing this key exchange, what you're essentially doing is, in both of these graphs, you're taking walks that are half the diameter, and then part of what our reduction result shows is that if you can actually find, so the probability that there exists a path between any two nodes is roughly p to the minus 1/2. So if you can actually find a path, then it's with overwhelming probability you have found the path that was used in the key exchange. So I wanted to just give a little plug for this group at Win4. So in case those of you that don't know, the WIN series of conferences, or the Women in Numbers conferences, which I co-founded and started organizing. The first one was in 2008, so they've been going for more than 10 years. And the next WIN conference is actually WINE3. It'll be the 7th one of these, taking place in Rennes in late August. And with Chloe Martindale, who I think is here, we'll be leading a group continuing to work on these kinds of problems. And so since this is a conference focused on algebraic geometry, I want to announce that the first Women in Algebraic Geometry conference is taking place in ICERM next year. And so especially for graduate students, it's a good opportunity, if there's any graduate students in the audience, to apply to that conference. So you should see the deadline announcement coming up sometime soon. Okay, so let's see, how much time do I have left? Almost out of time. So in conclusion, what I wanted to say is that I'll leave you with a kind of a summary of a lot of the ongoing work in this area, much of which is being represented at the special session going on, Isogenies in Cryptography. So obviously, I'm not giving the whole program for all the talks in the special session. But when you think about mathematics and cryptography, you should think we make up hard problems, we study how hard they are, and we try to break them. And then we also try to implement them efficiently. And so isogenies in cryptography, what you're seeing is all of those aspects of the problem still being represented. So some talks that are about alternate graphs and protocols, two-dimensional analogs, signature schemes, new attacks or different types of attacks, understanding the underlying graph structure, et cetera. So I encourage you to go and see some of those talks, and I thank you very much for your attention.
Thank you, Kristin, for an inspiring talk. Are there any questions? Please ask questions. I'm dying to throw the dice. No questions? Yes.
Okay. So thanks for the talk. It was really great. So maybe I missed it, but which part of the super isogeny singular graph-based cryptography makes it quantum resistant?
Oh, I didn't say anything about that.
Oh, okay.
So of course, we don't know that any of these things are quantum resistant, because maybe somebody's going to come up with a polynomial time quantum algorithm, but they haven't come up with one yet. So the best known, at least the last time I checked, I hope I'm up to date, so for supersingular isogeny graphs, there's a p to the 1/4 quantum algorithm by Bias, Zhao, and Sankar. Did I get that right? 2014. And that's the best known quantum algorithm. But you're kind of asking, how do we know? Like, why would we think that it's quantum resistant? Well, in the ways in which the quantum algorithms have been deployed so far is using, so actually Dan Bernstein gave a talk on this the other day here, using the hidden shift problem and the kind of the commutative structure of like the commutative group structure that you have. And you don't have like a commutative group structure in this in this setting. So if you look at, so the other major contribution of the Win4 paper that I pointed to, that I cited here, was to describe these graphs, to describe these graphs in a slightly different way. So you can think of them as being arising from, it's fairly complicated, but it's like a double coset space of adelic points of some algebraic group. And even though it looks a little bit horrible, what it shows is that there is actually a group action there. It's just a non-commutative one. And so there's some hope that, like, for example, if you can get polynomial time quantum algorithms for some non-commutative groups, that could potentially be an approach to attacking this. But even that description is assuming that you've taken the other description of our graphs, which is in terms of maximal orders in a quaternion algebra, the class set of that. And it's very hard. That was the paper co-authored with Christophe Petit and others from Eurocrypt last year, showing that really the hard problem is actually going back and forth between that description of the graph and the elliptic curve description. So sorry, it's a little bit of a long answer, but it's saying, all I'm saying is we just don't know better quantum algorithms right now. And the ones that we kind of know how to do in other settings don't really look like they're going to work here. So that's my best answer.
Thank you.
Any other questions?
Yes, so compared to other post-quantum cryptography like lattice or multivariate, what is the advantage and disadvantage of the isogeny?
What is?
Compared to other cryptography like lattice or multivariate, and what is the advantage of the...
What is the advantage of these systems?
isogeny,
Okay.
yeah.
So I would say that the main advantage in very broad strokes is that the key sizes are relatively small. They're kind of normal. They're like, elliptic curve crypto key sizes. Whereas key sizes for code-based crypto and lattice-based crypto can be extremely large. On the other hand, then the operations are more costly than in the code-based and lattice-based. However, there has gone, a lot of authors have worked very hard on doing efficient implementations in this context. And so even very impressive speeds on different types of processors and hardware to make the speed up. But I'd say the key size is probably the biggest advantage.
Thank you.
Is there, maybe we can take one more question, if there is one. Else, don't run away because we have a short announcement. Yeah, and before the announcement, we thank Kristin.
Okay. Hi, everybody. I'm Timo de Wolf from the Technical University of Braunschweig in Germany. And I would like to quickly announce that we will host the International Congress of Mathematical Software in the next year, in July 13 to 16. So this will be organized mainly as a main chair by Michael Joswig. We have 3 program chairs, and I will be the local chair. And so in case you don't know, Braunschweig is roughly 90 minutes by train to the west from Berlin in Germany. It's quite easily reachable, also from Hanover and from Frankfurt. And I'm quite thrilled that we have a collection of, I think, very stunning invited main speakers, and we will have a bunch of software sessions. The call will be open soon, and will be over the SIAM newsletter. And so please consider to come if you like software, if you write software yourself, or if you just want to learn about it. Please think about organizing a stream or participating in one.
or to present your software. So, and then I know probably the question by Cordian will now come up, but will I be able to see the midnight sun? No, I'm sorry, you won't. But still, I hope you consider to visit. Thank you.